Okay, here we are going to talk about the second part of the lab for the week of October 26th. We're going to look at exercise 19 from Contemporary Activities in Astronomy by Hoff and Wilkerson. And so what we're going to do here is we're going to look at the Doppler shift. And we haven't actually yet talked about the Doppler shift in class. As I'm filming this, we will on Wednesday, so half of you will do the lab on Tuesday and half of you will do the lab on Thursday. And so the Doppler shift says that when an object is coming toward you, when you're here and you're here, it doesn't matter which one of you is moving, but as long as that space between you is getting smaller or coming toward you, the light that you observe gets shifted toward the blue end of the spectrum. It's a shorter wavelength than what was emitted by the object. So if a star is coming toward you, the light that you see from that star gets shifted to shorter wavelength. If it's moving away from us, then it gets shifted to longer wavelength. And as long as the speeds are slow relative to the speed of light, and that's all we'll work with in this class, is to say that V over C, the speed relative to the speed of light, remember that's 2.998 times 10 to the 8th meters per second. The speed over the speed of light is equal to the change in wavelength, the shift in wavelength, divided by the wavelength. So you want to take the shift in wavelength, divide it by the wavelength, and that's going to give you the speed divided by the speed of light. So that's what we're going to be working on in this lab. We're going to look at Arcturus, and we're going to look at spectra from Arcturus taken 6 months apart. And so the theory there of taking this 6 months apart is you've got Arcturus out there, and Arcturus is either moving away from us or it's moving toward us, and we've got the sun here, and we're orbiting this way. If it's moving away from us, when we're moving away from it and it's moving away from us, our two speeds add up. If then it's moving away from us and we're moving toward it, the two speeds subtract from one another. One's causing a blue shift, one's causing a red shift, and we have to subtract them. If it's moving toward us, then when we're moving toward it, the two speeds add, and when we're moving away from it, the two speeds subtract. Take a look and see if it makes sense. Try to talk to your friends, work with people around you, and try to make sense of this box. This is a tough box in figure 19.1 at the top of page 154. So look at that box and see if you can make sense of what's going on in that box. To say, we'll see a line, and if the line that we're looking at, here's the theory. There are absorption lines in the spectrum of Arcturus. And so we're looking at those absorption lines, and they're shifted just a tiny little bit because we're moving relatively slowly relative to the speed of light. We're not moving very quickly at all. So these lines don't get much of a shift, and we have to work hard to try to measure these lines. And if you see 6 months apart like this, if you see both a blue shift and a red shift, if one of those times all of the lines are red shifted, and one of those times all of the lines are blue shifted, then that tells you the speed of the Earth is greater than the speed of Arcturus, because we're able to overcome. So suppose Arcturus is moving toward us, then when we're moving away from it, if we get a red shift, that means our speed moving away from it was able to overcome the speed of Arcturus moving toward us, and we're able to get a red shift. Now, it is possible that you don't see a blue shift and a red shift. You see only 2 red shifts or 2 blue shifts. Suppose you see 2 red shifts. Here's the line, the dark absorption line that you would expect to see in the spectrum of Arcturus, and we measure a red shift that is here and here. So the line is shifted this way, and the line has shifted that way by this amount and this amount. And so when we see those lines shifted by that amount, we see a bigger red shift and a smaller red shift. And the bigger red shift is going to be when the star is moving away from us and we're moving away from it. And the smaller red shift is going to be when the star is moving away from us and we're moving toward it. So in one case, this is going to be V of the Earth plus V of Arcturus. And in the other case, it's going to be, that's there. And in the other case, it's going to be V of Arcturus minus V of Earth. If you see both a blue shift and a red shift, there's the line that you would expect to see from the star if it were stationary. If it's not coming toward us or moving away from us at all, there's the line. And here are the shifts. We see a red shift and a blue shift. In this case, the blue shift is bigger than the red shift. That tells us If the blue shift is bigger than the red shift, that tells us Arcturus is coming toward us. If the red shift is bigger than the blue shift, Arcturus is moving away from us. But because we see both, the speed of the Earth is going to be bigger than the speed of Arcturus relative to the sun. So this bigger shift is going to be v of Earth plus v of Arcturus, and this smaller shift is going to be v of Earth minus v of Arcturus. Okay? And so now that's what you're trying to figure out. So there's a whole series of questions in the lab. I want you to answer those questions as it asks them in the text as you go through there about whether it looks like from looking at this, Arcturus is coming toward us or moving away from us. And then it walks you through trying to calculate this. What you basically end up with is two equations and two unknowns. The speed of Earth and the speed of Arcturus. The speed of Earth plus the speed of Arcturus is this. The speed of Earth minus the speed of Arcturus is this. Or the speed of Earth plus the speed of Arcturus is this. The speed of Arcturus minus the speed of Earth is this. And so you're going to, in these two cases, and you're going to get the speeds from doing this. And you're going to get the speeds by looking at the spectra that are in the lab, taking these 6 months apart. And so the spectra look like this. There they are. Boom. Okay? Now, do not ever do any measuring on this diagram up here. We just drew that diagram for you. That's not that's a finder chart. It's telling you what the wavelengths of these bright lines are down here in the laboratory. So this bright line right here has a wavelength of 4,282.41 angstroms. Okay, so we're working in angstroms here instead of nanometers that we often work in. And so you know that 1 angstrom is equal to 0.1 nanometers. So 4,700 and some angstroms is 470 some nanometers. So that's bluish green light that you see right there. So anyway, we're working in angstroms, and so you can see what the wavelengths of these bright lines are. Now, just as we had with the mass of the moon, this is a scale. This is just a scale of the spectrum. We could have made this anything we wanted. If the page was bigger, we would have printed this bigger and bigger and bigger. I could project it on the board, and we could see this spectrum projected against the board. We need to understand the scale of our spectrum, and we call that the dispersion of the spectrum. So what you can do is find the dispersion of your spectrum by measuring. Take your ruler and measure the space between two bright lines, say those two bright lines, and then calculate the wavelength difference between those two bright lines. Take this number minus this number and divide it by the actual space you measure down here. We measure on the picture, we read from the diagram. Read from the diagram, measure on the picture, and you should end up with a dispersion that's something like angstroms per millimeter. How many angstroms per millimeter is the scale of our spectrum that we've built right there? So you have that dispersion, and that allows you to calibrate your shifts. You will measure your shifts in millimeters and then convert them to angstroms. And to measure your shifts in millimeters, you want to pick 3 lines in here that you can see the dark absorption lines in the spectrum relatively clearly. So if you can see the dark absorption lines in the spectrum relatively clearly, choose those lines to measure your shift. And the way I would do it, if I were doing it, but you can do it however you want it, is that you have a dark line up here, and you have the dark line down here. You have the dark line there, and you have the bright line right there. I would take a ruler, some sort of straight edge, and draw a light pencil line that connects those two bright lines through the spectrum. And you're looking to see how far right and left that dark line got shifted. That's where you would expect it to be. It got shifted over there. So you're trying to measure right there. You got delta lambda. And you're measuring a shift in millimeters on your scale diagram. And then after you measure that shift in millimeters on your scale diagram, you use your dispersion to convert it to angstroms, and that's delta lambda. Lambda is whatever the wavelength of that bright line is, but you just read it off your finder chart in there in your lab. So you read what the wavelength of that bright line is on the finder chart, and you've got you got good shape here. So what I want you to do is I want you to work through all of this, measure the speed 3 different times with 3 different lines 6 months apart. So you're making 6 measurements. How much did the line shift one time one direction? How much did it shift that same direction more or less, or the other direction 6 months later? So you pick 3 lines and you measure from spectrum A and from spectrum B the shift of those 3 lines. Convert that to angstroms. For each of those, calculate delta lambda over lambda. So do delta lambda over lambda for each of those 3 lines, and then average your delta lambda over lambda to find your V. And in one case, you've got a V that's the sum of the 2 speeds. In the other case, you've got the speed that's the difference of the 2 speeds. And so then I'd like you to calculate the speed of the Earth and the speed of Arcturus. That's what I want you to do. Walk me through your process of how you're doing all of this and all your measurements. Report all your measurements that you make and tell me what you get for the speed of Earth and what you get for the speed of Arcturus. You don't need to do anything about this. Don't worry about this part F where you're finding the semi-major axis, the astronomical unit or whatever it is you're finding there. What instead I'd like you to do is to compare the speed of the Earth that you get to the known speed of the Earth in orbit, which is 30 kilometers per second. Okay, so the known speed of the Earth is 30 kilometers per second. Now it's going to vary a little bit because the Earth's got a little bit of eccentricity in its orbit, but it doesn't vary very much. And so what did you get relative to that? And then you're going to work through the discussion questions here, and it's going to help you think about that a little bit. So I'm going to say for this part of the lab, don't even do a paragraph write-up. Just walk me through all of these calculations and give me instructions about what it is you're doing with each of those calculations and tell me about it as you do it. And then answer discussion question 1 at the end of the book, discussion section 2, discussion question 3, discussion question 4, and discussion question 5. That's all of them. So do all 5. Instead of writing a paragraph after you've walked me through all of this, just answer all 5 discussion questions down through here. And they're all about these measurements that you made of Arcturus and the Earth, and about other kinds of measurements you could make with the Doppler shift. So we're going to practice using the Doppler shift to measure speeds. It's a little bit complicated by the fact that nothing's sitting still. We're moving in orbit. We'd love to just measure our speed in orbit by measuring the Doppler shift to order away from a star. But that star's moving relative to us too. So we got to take that into account and figure out how we can do this. And we can do it. That's the great thing about this. It turns out that we can make these measurements, and you're going to measure the speed of the Earth in its orbit and walk through the discussion questions to figure out what kind of corrections you need to make to take what you measured and get this 30 kilometers per second out the back end. That's what we got this week. It's going to be fun. Looking at spectra in lamps and bulbs and so on from exercise 9, and then from exercise 19, we're going to measure how fast the Earth's moving in orbit and how fast Arcturus is either moving away from or approaching the Earth. And it should be a lot of fun. So have a great rest of the day, everybody. And we're right now, as I'm recording this, you're taking an exam. I hope it's going well. And we will see you in lab.